Hi everyone, and welcome to my very first Substance Designer tutorial. Today I'd like to show you how you can procedurally generate this nice looking spiral pattern here. And we will be doing this by using one of the most powerful tools of Substance Designer, which is called the FX map. Now, you don't really need any experience with FX map, but just to explain, FXmap is a very powerful tool. It's very advanced tool which allows you to create very complex image effects, mostly procedurally, and by no means it is supposed to be intuitive, So it's not like the other tools which you can basically mix and match, connect with others, and immediately see the results. If you try to do it this way, you will probably be disappointed. So yeah, if you don't have any experience, I strongly recommend you to watch some official videos which explain in detail how it works. And of course, I cannot possibly explain it better than official videos. Yeah, but again, you don't need to be you don't need any experience with FXmap for this tutorial. Our use case will be pretty basic and I'll explain everything as we go. Yeah, so right before we actually start with this pattern, I'd like to explain why exactly does it look like that? What gives this pattern this special look? And for this, I'd like to switch to my browser and to this Wikipedia article about Fibonacci numbers. Of course, spirals have something to do with math, right? So if you scroll it down, way down, it's a pretty good read though. So, but yeah, just if you scroll it down to in nature section, you will see this sunflower head, and you can see that flowers here are also organized in some kind of pattern. And as it turns out, this pattern was studied, and one of the most important thing for us is these two little equations. One equation is for the angle of each element. As you can see, they are enumerated on this drawing. So every element is rotated to a certain degree, and then the other equation shows how every element is being moved from the center by a specified offset. So both of these equations actually depend on the number of iteration, and as you can see on this picture, this number inside every circle actually tells you what number of iteration it is. This is pretty cool. Yeah, so with this knowledge in mind, let's start. And let me just close what I currently have. And yeah, we will start with the new graph. I will not use any materials because I want just a grayscale map. So yeah, let me call it spiral, and I'll leave it at 1K resolution for now. Now, I don't really want this 3D view, so I'll close it. And yeah, let's start with doing some shape. At first, I'd like to create a petal-like shape. And let's start by using the shape node. What I'd like to do is to use paraboloid here, and I will scale it down horizontally like to 0.6 and vertically just to have a small vertical margin. And the way I will create this petal pattern is by using skew transform. I will also only use the grayscales, and we will skew horizontally to maybe like this. And then I would like a mirror which will just flip one of the sides of the image to the other side, and we will get this symmetrical like image. And what I'd like to do is to switch the skew from top left to bottom right, so that we can have this kind of shape, and you can adjust it the way you want it. I prefer something like this, for example. Yeah. And now let's just use another node to flatten this image so that we have the mask like this. Okay, that looks good so far. And this will be our base image, which we will be basically cloning. And just before we start with FX map, I'd like to create a transform 2D node to scale this image down. I will scale it down by down to 10% of the original image here. And one thing that I don't want to have here is tiling. So in order to disable tiling for this particular node, we have to go to base parameters, and as you can see, there is a tiling mode here, but it is disabled because all of these parameters are actually inherited from their parent nodes. So what I want to do here is to click this button and override it with absolute value. And now we can select no tiling, and here we go. We only have one single petal here. All right. And yeah, also what I want to do right now is to give it some offset on the Y scale so that it could stay just slightly above the center. So yeah, this will do. Now to the interesting part, let's create the FX map. And FX map doesn't actually have any useful parameters here. You can contain regions, styling, that sort of things, but they are not useful for our use case. The only thing I'd like to change is the mode, which is grayscale. I'd like it to be grayscale. And also I'd like to plug our image to one of the inputs. As you can see, there are two inputs, the background input and image 0 input. And yeah, I will be using the image 0 here. So, right, nothing can be done here. So in order to actually start defining our spiral, I have to go to this FX map editing mode, which is Command E on Mac and Control E on Windows. And this opens the inner graph of FX map, which is called Markov chain. And once again, I strongly recommend you guys to watch some other videos which explain it in detail. But what you need to know right now is that this quadrant node, this is called quadrant node, it actually has all sorts of parameters here, and for starters, we need to select our input image in the pattern parameter, so that we start to see our petal here. And also, it contains all sorts of transforms. It allows us to change the size of the image. It allows us to rotate it. It also allows us to change the blending mode, which will be very useful since we are actually combining multiple images. Yeah, but since our spiral is actually a loop, we need to start with iterate node, and not like this actually, because what it did is it connected this quadrant node to iterate loop. Not like this. I would like to create iterate node above the quadrant node, and also I'd like to make iterate node the root node. This is pretty important. When you select the root node, the orange background gets transferred to this guy, and so our input image first is first passed to this iterate node, and then we connect it to quadrant node. And yeah, also iterate has two outputs, which is also a bit counterintuitive, but the first output is actually called a bypass. So if you connect it to the first output, it will not get iterated. So only second output is used for iterations. I imagine for some image effects this could be quite useful. So yeah, let's start by changing the iterations number to say 6. And as you can see, nothing really happens. So in order to see some result here, we need to define the rotation function, because just changing the parameter doesn't change the fact that all of the 6 images get rotated to the same degree. So we need to introduce the function to control our rotation for each iteration. And this is where basically where all the power of FX map comes from being able to specify the functions for all these parameters. And this is exactly what we're going to do. So yeah, as you can probably remember, our function for rotation is just the number of iterations, which is n here, multiplied by this constant angle, which is 2 pi divided by phi squared, and phi is a golden ratio. So this is evaluated to approximately 137.51 degrees. And yeah, so this is exactly what we're going to do here. Let's start with getting the current iteration. And inside this pattern rotation graph, one quick note, you can go back and forth between those by just switching to different windows. And right now we are working inside FX Maps pattern rotation function graph. So this function graph accepts the output type of float1. And for starters, let's create a node which allows us to access the current iteration number. And this is done via the getFloat node. And in getFloat node, you have access to the $number variable, which gets set by this iterator node. So basically, for the first element, it will be 0. For the second element, it will be 1, and so on and so forth. Yeah, and we also need to create a float, not floor, oh, not floor, float constant, and let's just say it will be our angle multiplier. Let's start with 30 degrees, and let's multiply the two using multiplication node. As you can see, we connect. This is how multiplication is done here, and we see nothing so far. So yeah, what we need to do here is to set the output node of this function graph. As you can see, the warning tells us that there is no output node currently. So yeah, let's right click on multiplication and set as output node. Here, now it became orange, which indicates that this is now the output node of this function graph. And yeah, we did everything right, but it still doesn't really work. Let's try the slider. And as you can see, these petals start rotating, but it doesn't really resemble rotating by 30 degrees. And the reason behind this is that this pattern rotation node, which we have the function defined for, it actually expects the function to return the number of turns. So in order to convert the degrees to turns, we have to add this degrees to turns node. Unfortunately, it's not really documented, or at least I wasn't able to find it. So yeah, but the conversion is pretty simple. You just connect these nodes, and don't forget to set output node too. So now it starts resembling the actual rotation by degrees, and let's try 60 degrees, and yeah, this gives us the full loop. Now yeah, let's change it to this magical 137.51 angle, and now it gives us these uniformly distributed elements. This is a special property of this angle because golden ratio is irrational. which means that elements, as you start increasing the number of iterations, you can see that elements get spread uniformly, and since their Golden ratio is an irrational number, it kind of guarantees that no elements get placed to the same position as some other elements. So yeah, just let's crank it up to 64 and you will start seeing this nicely distributed circle. So yeah, but it's nothing exciting so far. So yeah, let's now continue with the offset. Unfortunately, it will be a bit more tricky and I will try to explain it to you, but nothing scary. So yeah, let's go to the pattern offset function, and as you can see, it expects the output type of float2, which is the vector with two components. So let's add this vector, and the first component will be the x offset, and the last component will be the y offset. And let me try to explain what's the issue here. So let's plug some constant number to the x output, and as you can see, if I start to move it, and yeah, of course, let's not forget to set the output node. I always tend to forget that. Yeah, as you see, once I start to move this, all of the images, despite their rotation, they get moved by towards the right side. So they all move on the x-axis, whereas we want every element to move in the direction of their rotation. Therefore, we need to calculate this direction. And well, the calculation itself is pretty easy. If you have some basic trigonometry skills, you probably know that the x position here is the cosine of the angle multiplied by radius, and the y position is sine of the angle multiplied by radius. So let's just do this. But yeah, as you can see, we still need this angle. So let's get back to our pattern rotation function, and let's get these three nodes which describe the angle of each iteration. We don't need to grab these degrees to turns. And let's copy selection. And let's get back to our pattern offset node, and we will paste these here. So this will give us the angle. Now we need to evaluate the cosine for x and sine for y of these angles. And one more note here is that both cosine and sine nodes actually expect the angle to be in radians, not in degrees. And the conversion is also pretty simple. You just need to convert degrees to radians, and don't forget to do that, otherwise you will have some weird numbers, weird positions and offsets, right? So now we have cosine and sine, and we need this radius. And let's get back to our formula. Here, the radius is evaluated as some constant number multiplied by the square root of current number of iteration. And let's get this number of iteration first using getFloat. And you need to specify the dollar number here again. By the way, yeah, we already have this, but I just decided to, copy it just to make it a bit more clear. Of course, you can just plug it directly from here, up to you. And now let's have the square root. And finally, let's have the constant, which I will give some small number, and let's multiply those. Now, this multiplication is basically our radius. And what we need to do finally is we need to multiply cosine by this radius. I'll add the multiplication node here. And we also need to multiply sine by this radius. And not like this. Sorry for that. Yeah, like this. And I'll plug my radius to both cosine and sine. And finally, we feed cosine to the x of our output. And whew, something starts to happen, right? And we feed sine multiplied by radius to the y. And yeah, this is what we get. Not quite resembling spiral, right? Yeah, but as you try to decrease this multiplier here, this constant, you can see that the elements start to converge towards the center, and this actually means that our spiral is kind of ready. This is our spiral. Yeah. Now, yeah, let's get back to this transform 2D and let's see what we can get by just playing with the initial offset. As you can see, when I move my shape towards the center, and if I basically position it right to the center, you can see that our petals or our seeds, I don't know what it is right now, so they get distributed more uniformly, whereas if you try to offset them, you can see that the gaps between these elements start to increase. And just to demonstrate it, let's lower this number maybe to 0.025, and maybe let's also crank the number of iterations to say 150. And by the way, please be extra careful with this number of iterations. If you accidentally type the large number here, the whole thing will probably hang and your work will be lost. So yeah, it's just a warning here. All right, and as you can see, if you move it from the center, you will have some gaps, whereas if you start directly from the center, the whole spiral gets distributed more uniformly. Yeah, that's great. And basically that's it. You can play with other numbers, values, try to maybe rotate it so that you have more like petal-like distribution, or rotate it 180 degrees so that you have this inward type of spiral. Up to you, and I strongly encourage you to play with all of these parameters. But yeah, let me just show you what can be done. Maybe let's plug this image to our node, and let's see what we have here. This is kind of nice, but I think that the blending mode in this FX map is a bit incorrect. What we could do to make it right is we could change blending mode inside quadrant here to max, and by doing this you will have more realistic kind of pattern here with some depth added. Yeah. So one more thing that I can probably show you is that we can blend gradient to our original image to emulate some kind of a slant. Let's try and do this, and we will just use multiply blending so that we have a shape like here, and we also just decrease this level just a bit. And yeah, let's plug it back to our transform 2D and let's see what result we have. Yeah, so pretty much what we have started with, what I have in my demo. Now, yeah, and of course, you can still use this transform 2D to play with the parameters. As you can see, for example, rotation changes the orientation of all the elements. So this is quite a nice thing to play with. And yeah, that's pretty much it. Now, one more final thing before we wrap up. Let me just do it again. I will replace my my input image with the white mask, and I will, inside my FX map, I can also define the function for luminosity, and probably I can also add variance to sizes. This is entirely up to me, up to my design decisions. So let's go to the luminosity graph, and for this let's try to just randomize all these luminosities. We should create a random luminosity from 0 to 1, and let's just create a random node here, and let's mark it as output node. And as you can see, you have some kind of foliage-like pattern. And let's try to give it a bit more spread by playing with this constant parameter. And yeah, as you can see, you can achieve some kind of foliage-like patterns as well. So let's see how it looks when it's styled. Yeah, something interesting, right? And that's it. Thank you for watching, and if you find this video useful, please subscribe. See you guys later.